Yeah, that was the original item. It's now subtitled questions I should have asked as an undergraduate and did not. Yeah, thank you. Before we started, I actually had thought of giving a talk on another topic called entanglement and superconductors. And ironically, I just opened it as I was waiting. I got an email this morning to say that my paper, Spin Entanglement, a Unifying Principle for Superconductors and Molecular Bonding, has now been published. And you can find it in online under a journal called Recent Progress in Material Science. So I didn't expect it. It came out ironically because of an email that Andreas sent me in September. He was working on a book in superconductors, and he tried to get me involved, and I ended up writing something which I decided best not to publish with a book. And then the same day I said, look, won't do anything with it. I got an email from this group, asked me if I'd like to send them an article on solid state physics. I said, what? Strange. I have this article. I'll just send it to them, which I did. I had to touch it up a bit and meet the specs, as you know, so they had a deadline of December 31st, and I sent it to them by December 20th. And finally, now having battled, one referee was full of praise and the other had to battle, but finally they've gone with me and published it. So I'm glad that's over. So back to the topic, action functions and Lagrange's equations of motion. This grew out of, where do I control? Here. What I can control you if you say next slide. Oh, yeah, okay. We can see the next slide. Lagrange's. So next, Lagrange's equation, some consequences of a lemma. Two examples: Hamilton's second equation of motion, and say a few comments on quantum mechanics. I hope this really is at the undergraduate level, because and find it a bit entertaining. But what I found actually surprised me. It grew out of the fact. Next slide. You're all familiar with Lagrange's equation and how we derived it. I grew up in Dublin, so my first introduction to Hamiltonian mechanics, Hamilton was from Dublin, by the way, was when I was 19 years of age, and you're introduced to the calculus of variations, and you're kind of in awe to see this stuff works, and you come out with this generalized equation, and you think you've discovered something very big, or you know it's something big, and it's almost beyond you. And I certainly didn't feel like I could ask questions or was able to, but there was always something that bugged me, because part of my professor, with the book that we used for our undergrad was mainly Singing Griffith's Classical Mechanics, and of course also references to Whittaker and so on, and Goldstein. And you're always told to meet you, well, think of Q dot as an independent variable, Q dot, and T. So it's like a 2n plus one dimensional phase space, and you then perform the variation calculus. You do an integration by parts, and this is Lagrange's equation. Then you, of course, can define, which I'll do for you in a moment, the Hamiltonian part of it, and you break it up into two single equations. And we're all familiar with that, okay? So I think you're familiar with the steps, right? It's you break it up. Oh, the T is not explicit. I took out the T just to make life easy. And so you take the integration by parts. And of course, the key always in the calculus variations, you fix the endpoints. And of course, you integrate over and you fix the endpoints, you can throw away that term at the beginning. And since this is arbitrary, then it reduces to this for an arbitrary variation. Okay, so I learned that like everybody else. And of course, next slide, we learned to not only that, write down Lagrangians, and we learned how to solve equations of motion. That looks very fantastic. But there was always something in my mind, which even in the early work, somebody had noticed that P was del S del Qi. And it never went anywhere. You just, oh yeah, well, we don't really work with characteristic action functions. The action function is delightful. It would be great if we had them, but they're too hard to find. Singh says they're better to start with action functions if you can, but they're almost impossible to find. So physics favors Lagrangians, and you work with the Lagrangian. However, I just noticed a simple little thing. If P is equal to del S d Qi, we also know P is del L d Q dot I over in the phase space, but it's the same P. They're not different P's. It's the same P. So if that's true, I can substitute, well, the del L del Qi, up here, P is del L del Q dot I. So what's the first part becomes, And then notice the L is by definition ds dt. That's how you define L. It's actually the definition. So del L del Qi is del Qi del S dt. Next slide. So what do we end up with? I'm surprised. That Lagrange's equation is nothing more than an inversion of total derivative with a partial derivative. D dt del S del Qi equals del Qi ds dt is true if and only if Lagrange is true. Now, it's trivial. It's a bit like what Bruce is saying yesterday. The result is so obvious. I don't know how I never saw it before. So I start looking up the literature, and I've never found that in any literature. Do you know of any? Admon's book, this precise result. Okay, which book? You can show me afterwards. Okay, because I looked at it, I couldn't find in the books I was looking at. So I was just intrigued by it. So there was the first lemma. So the proof follows by substitution. Next slide. So the next thing I notice is, of course, if that's true, then we have an we have a pure commutator on S. The total derivative times the partial derivative action on S is a commutator and defines an equation of motion for any action S. So you end up there that the commutator of the total derivative and the partial derivative of S equals 0 if and only if. Now, there's an equivalent condition. I expanded out both sides of the ddt, the total derivative, the partial derivatives, and you keep, now you're working in coordinate space. That's important to remember. Working coordinate space, you're not working in phase space. Otherwise it'll be. So working in coordinate space, so therefore the q dot j is in coordinate space, so it must be a function of the q's and t's. And so there's the equivalent of your equation of motion. And then you can do something else. You can go ahead and then you can take the derivative. Remember, P was del S del Q, so P dot derivative in coordinate space will be just this. And of course, this is your definition of the Hamiltonian. Hamiltonian is del S del Qi minus in coordinate space, so it's minus del H del Qi. So you want to get Hamilton's equation of motion. I'm not saying it is Hamilton, but if you insist on this, that can only happen if this is true. So there's an if and only condition for Hamilton's first equation, right? In coordinate space. Next equation. So again, I take back to Lagrange's equations. So plug it in, d dt del L del Q dot I equals del L del Qi equals del L Qi, if and only if there's the Lagrangian defined in terms of the Hamiltonian. That's who was that first discovered that? Was it Lipschitz or who was the mathematician first wrote down the transformation? But anyway, I've forgotten. And again, you want, well, the d dt del Q dot I is just P dot I equals that. Therefore, Hamilton's equation of motion implies this equals minus, which is if and only if this is equal to 0. Right? Otherwise, it's not going to work. Again, coordinate space, coordinate space. If you're in phase space, you see they're all independent. So because they're independent, they're all equal to 0. But you're no longer. So what happens? Independence of pure. Now, if they're independent, well, they're technically independent because PJ is defined in terms of the if the Lagrange. Remember, it's just del L del. No, in terms of the action, ds dq. That's it. There's no reference to time. Q dot means it's a time variant going in, so you've got a lot of flexibility on how you want to find Q dot. So there's an independence there. And so in that case, this equals this, and you end up with this result. Implies this is true if and only if both of these are individually 0. And if you wanted to relax that condition of forcing them together, you could probably get a slightly more general result. So they're just different equivalent ways of writing Lagrange's equation. That's all I'm saying. All of these are if and only if and only if and only if. And various forms. Just the fact that you can think of Lagrange's equation as DDS partial derivative equals partial derivative D, or not DDT partial equals partial times DDT of any function. That's a Lagrange's equation. And which to me was quite remarkable. Now, the actual original Lagrange, when he discovered the equation, was talking about you're looking for a curve in real space where if you release the particles simultaneously, they'll both reach the same point at the same time for all points. It's interesting under gravity, right? Sorry?
Transition to Hamiltonian form holds only for
Okay. I mean, I know, I know of the original putting convexity, and they've tweaked it. You start with convexity, and then you can move it on beyond that. I didn't go into those conditions, but you're perfectly correct. Next. So a natural motion, I just put it in. Now, that's not the full definition of a natural motion, but I just put it in for the moment. And a motion is called natural if and only if the total derivative of ds del qi equals delta qi del s dt, and the other way around. Now, here's what I've thrown in. The one I went, if we go back, the original definition of Lagrange only had the coordinates involved. They didn't put the time in. If you put the time in the same condition, you get a very instant results. You essentially end up getting a constant of the motion. So it turns out that this equals zero now over 4 parameters, and it's you could almost call the fourth parameter H0, and you can write it more explicitly in this. Actually, it's actually invariant on the coordinate transformations rather than just Minkowski. If you want to write it that way, HT minus, there's your thing, and this I just was thinking of Lorentz transformation. It's manifestly Lorentz, but actually, the more I look at it, it's actually coordinates. It's invariant on the coordinate transformations. So again, so putting in the extra condition about the Hamiltonian, that would be equivalent to the other equation of motion. If you explicitly use the Hamiltonian, put in the time parameter, you're all familiar with the fact that the total derivative of a Hamiltonian equals del H del T. So that's this condition here. So if you put in that condition, you end up at the P being a constant of motion, which is really basically saying energy is conserved. That's what it really amounts to. Next. So, and I just gave a couple of examples. Now, I wanted to be a mathematician here. I just put something that has no physical meaning. So you take ds, take s to be the qm over tn, and I just ran them through. Then I took the derivative del s del t, which would be your Hamiltonian or your negative Hamiltonian. P equals del s to qi would be this, using definition of the natural motion. Remember, in other words, all inverting total derivatives with partial derivatives. You end up with these equations, from which it follows q there's a constant of motion. Also, you get this result. And in this case, then you have the following. To keep it consistent, this has to be 0, which means this too is a constant. Also, when m equals 2, you get back classical, you get physics, h is a constant of the motion. Which, so just an example. Now that's just one term that's just one term in the action function. And I should just probably comment now, because before we get to the second equation, if I invert, instead of solving s and q and t, I was to switch, and we define p. Remember, p by definition is del s del q. If I was to turn that around and write q in terms of p rather than p in terms of q, and then write down s, substitute back into s, it turns out you won't get p, you won't get, here we got p equal to del s del q by definition. But if you invert it, you won't get q equal to del s del p. You'll get q equal to some constant. The only time it's actually equal when it's quadratic, which is interesting. So when you do a full, if you want to be symmetrical between the p and the q, in terms of p is del s del q and q is del s del p, you need a quadratic. Otherwise, you've got to counter with a constant. Okay? And that has repercussions too. So again, now I'm just taking a very simple example. I wrote let s equal to minus ht, I'm putting the t, where such that h is fq1 plus gq2. So I'm putting in 2 coordinates. Then certainly h is equal to, then clearly h is equal to minus, also, it means also that p1 is f prime q1 of t, and p2 will be g prime q2 of t. And h0 is, let's call this minus ds del t equals ht dot. Now, it's a very precise example. There's only one term with h basically being a constant term. Though I'm not saying h is yet constant. For this to be a natural motion, we require you just take your definition, plug it in, which I did before. It follows that in this case, it reduces to this, which means HQ is a constant of the motion, which you're not surprised, it's a Hamiltonian. Okay. So note there's very little, no, but the real thing is there's very little structure here. All I've done is said H is made of 2 coordinate functions, Q1 and Q2, no other, and they're summed, so there's a nice case. gone ahead and we've ended up with a constant of the motion. Now, where does Hamilton's second equation come in from? Because when you're used to the calculated variations, first of all, using the transformation, the convex transformation, which was originally used to change Lagrangian into a Hamiltonian, the convexivity can actually be relaxed. I've forgotten all the conditions for it, but the mathematicians work in those things and you can tweak the convexivity. But anyway, let's say having basically just wrote down the Lagrangian, you switch it into a Hamiltonian, then you do the calculated variation. We normally get two equations of motion, right? We've only gotten one. We thought P equal del S del Q. I differentiated it. P dot equals, and you force it to coincide with Hamilton. Now, to get the other way around, you've got to do some work. You could have said, well, solve it in reverse. If I have a system of equations solvable in Q and I invert them for P's, I can invert them. If they're invertible, I can solve them for P's. But it doesn't quite work that way. Even for one parameter alone, it won't work unless you've got a very precise P. So next slide. So equation 3 above gives H equals HQ1 FQ1 plus QGQ2, a constant of the motion. It does not specify whether F and G represent two independent particles with constant velocity. That's another way to look at it. FQ1 could represent the motion of one particle, the Q1 parameter. The GQ2 could be another. Or it could be one particle with two associated conjugate states, which is what I want to get to. So if they're dependent upon each other, well, then either way you have this equation. Just take a derivative, it's a constant of the motion. By the way, this generalizes for Qn. I think you can see that. I'm just using 2 to show you the point. Clearly, now in this case, we define Q dot is here and Q1 is here. We'll give a set of solutions. Okay, just mathematically speaking, if you define Q dot 2 to be minus del H Q1 and Q dot 1 to be del H, we will get a set of solutions. Nobody's saying they are the only solutions, by the way, but they certainly will. One will force the other. And equating, so suppose we say, but Q2 is really, we'll call it P1. From a mathematical point of view, it's only change a variable. Of course, now we're thinking quizzically, but you've jumped into momentum. It's true, but mathematically, I'm just calling a variable. So if Q2 is Q1, there's the two Hamilton equations of motion. So that tells you there's a lot going on in physics when you switch to two equations. First, you have a Lagrangian. The Lagrangian is a much looser structure. The integration by parts and fixing is done something similar. It's really assuming the almost equivalent of a constant of the motion, which is the Hamiltonian. It's because of the constant of the motion. Now you can say, but there's the dH dt equal to del H dt. But I've already ruled that out. Remember, that was my fourth condition. So that cancels out. So basically, you've got a constant of the motion, and being a constant of motion forces the second equation. That's really what's happening in terms of Hamilton's second equation of motion, which is fine. So, but that's really what it's about. So these are Hamilton's equations. Note, this requires that both F and G have to be quadratic, if in the case of a harmonic oscillator, for example. It's interesting that most equations you see in Lagrangians always seem to have quadratics in it. Rarely do you see something that's not quadratic. And once you're with quadratics, you're pretty safe, I assure you. There won't be anything going wrong with the math. Next. So so now I want to, so there's a duality between P and the Q. That's the point. We had Lagrangian was in coordinate space. We took partial derivatives, we got momentum. But if I had, instead of worked with a coordinate space, I'd worked in a momentum space, meaning worked with P's rather than Q's. Now, you could say, but that's just a change of symbol. Right, there's also a slight change in the Hamiltonian. Rather than saying that the Hamiltonian is negative del S del Q, you need to find P equal to positive del S del P. And the factor explains the switch in the sign that actually happens. So P equals minus del H del Q if and only if this is the condition, which I showed. That's the Lagrange's equation. Or you could have worked this way. Q dot del H and just worked with P's. Okay? And so here's your second equation of motion. So you have, and now that should remind you of in quantum mechanics between coordinate space and momentum space. It's exactly the same thing that's happening. It allows you to see the parallels. And if you really started with these and forced these, then you could actually derive that, which we had. But I put this in originally, so you would have gotten that. So they're all interrelated. Basically, if you fix two, you'll get the third. That's what I'm noticing. You got kind of three conditions. Put two, and you get the third one out. It goes around the circle. Okay. I'm just noticing the date. I have no idea. So because I pulled up a template from the last IARD, that's what that's amounted to. And anyway, so let's reconsider. I want to do something about what. Here's my point. If that commutator, and that's two operators on S, is equal to zero, where does quantum mechanics come in? That's a classical equation. I'm claiming that's equivalent to Lagrange's classical equation of motion. So at this stage, where's quantum mechanics? And secondly, I think it's a bit more elegant. I like to see that written down because normally we show the parallels between classical and quantum by referring to the Poisson brackets, right? But this is not a Poisson brackets. That's because you're using H. The Poisson brackets, I'm using just S, and I got a pure commutator. And it's classical. You can't say, well, that's quantum mechanics. No, it's not. It's classical. So I want to explore, where does quantum come in? And if so, how? And maybe that would be helpful also for an undergraduate, a question I should have asked as an undergrad. First of all, note that commutator is even only for any function of S. You can work around the homework exercise. For any function psi of S, including for say, an eigenvector, that's true. Okay. So it's a bit like the wave equation for light, the general definition of, you write down the wave equation for light or for any wave. And the general solution is f of x minus vt plus gx plus vt. It's almost similar. Once you have double derivatives, you can almost get a general solution. So it's actually, psi of s is actually a solution for any size, any function. I'm anticipating quantum, so I use psi. I could have used S. And it could be an eigenvector, but it doesn't have to be here. Okay? But you can't use eigenvectors. And moreover, use eigenvectors, they have simultaneous they're simultaneous eigenvectors, obviously, because it works for any functions. So, moreover, when psi is an eigenstate, then the commutativity means that both operators have the same eigenvectors, but not the same eigenvalues. Indeed, the commutator equation relates the different eigenvalues into a system of equations that defines the motion of the particle. So the particle motion is actually defined in terms of the relationship between the eigenvalues. If you were to look at just go back to at the end, the eigenvalues of the et or dt, ds are actually going to give you an equation of motion. So it's the relationship between the eigenvalues is giving me the equation of motion for the particle. So, but that's classical, no quantum so far. You're right, I agree. So where does the quantum come in? And that got me thinking. Well, the reality is, because of the uncertainty principle, which, we have two derivatives here. Now, if I took out the ddt or the delta qi and put in just x, you get the uncertainty principle, right? So that's the first thing. Because the uncertainty that is valid for both operators, we can never measure the constants of the motion. And that's where real physics kicks in, distinct from the mathematics. Physics, as most of you are talking this morning, depends on experimentation. And there's a limit to how far you can get down. And when you go down too far, you're just, no matter how good your equations are, you just can never get enough information to pin down the equations of motion. There's too many constants, and those constants are basically up in the air. Think about a planetary. If we didn't have telescopes, we wouldn't be able to work out or radio telescopes or lasers. You couldn't know anything about the motion of the Earth around the sun. It would be very hard. So it's a bit like that. So quantum mechanics then really comes from asking a different type of question, and that's what I'm trying to get to. And it brings up some interesting philosophical points and some real physical points. Quantum mechanics doesn't ask what is the equation of motion, because in principle it's saying because of the uncertainty you'll never get to that equation. You can write down a generic equation, get the eigenvalue equation, here it is, but there'll be a lot of constants in there, and you'll never be able to pin those values, maybe in some rare exceptions. So it becomes physically meaningless, even though mathematically you have something. And we were all aware that in classical mechanics, many times you learn Newtonian mechanics, you integrate out or differentiate, and you solve the equations of motion, you put in the boundary conditions, and once you stick in the boundary conditions, you now have the information. The problem is with the quantum is you can never say what the boundary conditions are. There was a book called The Foundations of Physics written by Margano and Lindsay and Margano. And they make the point of the value of boundary, the importance of boundary conditions in physics. And I think that makes the first point. So quantum mechanics then is asking another question. And that's probably helped you to ask. When I'm asking, it's almost a statistic. It says, look, you can't know what the equation of motion is, or you can in a way that's irrelevant. So, but I can now ask, but how many eigenstates are there and what are they? So now, once you ask a what question, how many eigenstates are there? What are they? The how many is always a statistical question. And if you teach probability theory, which I've done for years, I mean, it's that what question turns out, well, mathematized, how many is not just a number. Normally you give a distribution, which allows you to make probability predictions about the number of possibilities. So that's really, you've changed the question. You're now saying, okay, how many eigenstates are there? Because the eigenstate, also think in terms of, think of linear algebra. What's an eigenstate actually tend to do, roughly speaking? It tends to be the axis of rotation or a fixed point around which things happen. If you were dealing with the rotations of the Earth, the eigenstate would be the Earth's, the axis of rotation. It doesn't change when everything else is moving, right? So basically, that's an analogy. So by analogy, all the eigenstates tend to be a fixed axis vector around which the action is taking place. And which in physics point of view means states of equilibrium. Once things are in equilibrium, you got them. So you're basically classifying states of equilibrium, which we're calling the eigenstates or energy levels or whatever, right? We're never actually saying the particle's in that energy level. We're just saying this is a possible energy level, this is a possible energy level, this is a possible energy level. So next question, next slide. So back to quantum. Well, quantum mechanics does not merely seek the eigenfunction solutions of the above operators, but also requires them to be L2 functions. And that's huge. I didn't realize in the last few months that how big the switch to an L2 function. And I think it's at the core of the EPR paradox. I'll explain that to you in a moment. First of all, this means that we're defined, an L2 function is a Hilbert space. Because it's a Hilbert space, we have an inner product associated with them, normally denoted by the bracket notation, psi psi. It's an inner product. Now we want an inner product's a number. Sorry? No, I'm trying to show you well, that connects. That's my question. At this stage, no, you never get a philosophical point. At this stage, this is obviously going to be invariant under rotations. It basically is invariant under unitary operations. So unitary operations automatically come in by just trying to maintain an inner product to be invariant. Okay. Now it's a bit like Kepler's came out yesterday. Just all mathematical operators necessarily have physical meaning. No, I mean the amount of unitary operators that you can put in, I defined it this way because the physicists do, but you actually can define infinite amount of parameters to a unitary operator if you enlarge your space. Some of them don't have any physical meaning. We usually take this one here, and now back to your question about the H. What is an H? From a pure mathematical point of view, it's only a scale of measurement. So it's like meters, centimeters. I'm using units of H. In fact, in physics, you like to talk about natural units, H equals C equals 1. Now, the philosophical question pertaining to ourselves, it's not just any unit, it is a unit, but it seems to be a unit that is preferred by nature. Boom. I mean, H came out of physics, it didn't come out of mathematics. So there's the different perspectives. A mathematician doesn't say, well, it's just a scaling, which it is. But it's not just any scale. It's a preferred scale that nature seems to be giving to us. So we're using it. So that's the first thing. So first of all, unitary operations is now a key term. That's not in classical physics. There's no reason why classical physics has to be unitary. Okay, we don't really talk about inner products. The action function, by the way, at the end is the wave function. So action functions are wave functions, but they're wave functions on an L2 space, which forces unitary conditions. And then the physics forces in the H, and we start looking at relevant unitary operators. We don't just take any mathematical unitary operator we can think of, which is probably one of the reasons why I would be critical of string theory. You have the impression string theory just plug together new dimensions. Every time you have a problem and create a new dimension, you can always make them unitary, just string them on, no pun intended, and you can get away with it, okay? But the real question is, and I think that's the balance between pure math and physics, can we pick those parameters that have physical meaning? And obviously H is one, and H bar is another. So that's it. So H is a scaling factor, mathematically speaking, but it's a physical scaling factor, and that's from the physics. Okay, next point. Normally, a general state is written as a superposition, where this is the probability theory, comes to getting the squaring. Now, that has consequences, and I'm almost finished. Next. And I won't go into the details, but if you think of the Einstein-Podolsky-Rosen paradox, Einstein believed that basically he rejected quantum mechanics because what we'd say nowadays are hidden parameters. In other words, let me give a simple analogy, writing down three. If I want to draw a circle, right? I just take a compass, draw a circle. And I can say, well, make me two of them. So I take the same compass, I draw a second. And I take a third, I can take a fourth, fifth, sixth, as many as I want. The hidden parameter is the radius and the fixed point. Once I have the parameter, I can just draw as many as I want. So Einstein's perspective, I'm putting in my own language, is basically saying, look, the spin nature of each of those particles, in this case spin, is determined by a parameter analogous to radius, right? So if you had a three-particle state, or just even one particle in three states, because from Einstein's perspective, the spin was determined for all angles by a hidden parameter. If you were looking at three different states, you could probably expect to write it down this way. Okay, so next slide. Now, as it turns out, I'm not going to give a talk on the EPR. I've done that, and I did do that here at IARD in the past, so I don't want to go into all the details. But if Einstein's hidden parameter viewpoint had been correct, then for an event A, we would have written a marginal distribution over for example, over the second term. Take spin up, spin down, would be just up, down, and so on. You'd pick those laws. You'd also expect from classical physics the Chapman-Kolmogorov equations to be valid, which you mentioned this morning. They're standard stochastic equations in any course in probability where you've matrices, right? Now, what happens in quantum mechanics because of the L2 property? It turns out, if you go back to my three circles, we can go back slightly. If I were to rotate the A1 into A2, there's an angle, and then the A2 into A3. If you're thinking classically, well, the rotation from A1 to A2 times rotation A2 to A3 are just it's just a product of two matrices. So R12, R23 is equal to R13, standard linear algebra. Okay, go ahead. So that's what's happening so that's this equation. Now notice that's very similar to the Chapman-Kolmogorov equation. However, these are not probabilities. These are just pure rotations. Now what's going to happen when you put a probability in? Now this part is linear, so when you square something that's linear, you lose the linearity. So next step. So in fact, if you switch them here, here's what you're getting in terms of rotations, okay? So next step. Next slide. Here's what happens when you switch the probability, because you're squaring. You get cosine squared is not equal to this. This would have to be true if it were Chapman-Kolmogorov, but it's not. So the Chapman-Kolmogorov actually breaks down in this case. And I think it probably breaks down in a lot of cases. And it's because of the L2 property. Therefore, the Chapman-Kolmogorov equations are not necessarily valid for quantum probability. So briefly put, the Einstein model anticipates that the Markov property applies, whereas the quantum model anticipates this, and they are not compatible because of the squaring process associated with quantum probabilities and L2 functions. So, thank you. Just an introduction to hopefully quantum mechanics, or a way of looking at quantum mechanics that probably helps you understand why quantum is not classical, but learning how to ask different questions. And I suppose as an undergrad, I knew there were some things I'd like to ask, but I didn't have the ability to ask, or we didn't have yet the tools to ask the right questions. So that's all my talk.